anybody has any AMS business to take care of, you can do it during the Q&A, just go back quietly. We got raffle tickets, last call for raffle tickets, last call for any ballots. If you haven't got your ballot in, it's gonna be too late in about 30 seconds. And you have a different question or a Q&A question? I think this is a pretty docile crowd here. We were gonna have Bobby stand right here with Mike, but I think we could probably take a handheld around and we'll pass Mike around.
Okay.
All right, who's got
Happy to
questions?
answer questions. Yes, we'll start there.
Cliff, you emphasize,
Got it, hang on a second.
repeatedly the trend in increased horizontal resolution. What about vertical resolution?
That's a good question.
Yeah.
We are in parallel increasing vertical resolution. You have to do that to a degree. But the interesting thing is, it turns out, you don't have to scale it 1 to 1. You double the horizontal resolution doesn't mean you have to double the vertical resolution. But we are increasing the vertical resolution in time, particularly in the lower part of the atmosphere, trying to get a boundary layer work right. So we are doing that.
How many levels typically?
Well, it depends. Right now, we're running 38 levels in WRF. The weather service for some of their models are running in the 60s. Okay, something like that.
Next question. And if you can, identify yourself for document.
Okay, thank you, Cliff. I'm Richard Rennie. And how do you feel the climate models are off? You refer to that. And they're kind of a different animal from your weather models because they're about averages as opposed to specific things.
Let me talk about climate. One question that people ask, we'll start with this, is some people say, how can you possibly forecast climate if you can't forecast the weather more than 2 weeks ahead? Isn't that an interesting question? Okay, we lose forecast skill at 2 weeks. How can we possibly forecast 50 or 100 years ahead of time? You want to know the answer to that? Who's ready to answer that? Well, I'll tell you what we can do. We can forecast the weather in 50 years from now or 100 years from now, and we don't even try. Forecasting the weather is trying to say, the front's going to be there. The low is going to be there at this time. We can't do that in 2070. What we do try to do, and we can do to some degree, is forecast statistics. What will the average temperature over the summer be? Or what will be the mean precipitation? That kind of stuff. We can forecast statistics, and the reason we can do that is that the nature of the forecast changes. Weather forecasting is what we call an initial value problem. You're dependent upon the quality of your initial state, and so eventually you lose skill. Climate modeling is what we call a boundary problem. Basically, if we know the radiation, how the radiations could be changing coming into the atmosphere, we can forecast mean things, like what the mean temperature will be, what the statistical nature of the atmosphere should look like, being forced by that. We can't forecast weather, but we can hopefully have some skill on what the mean state of the atmosphere is going to be like. Now, the trouble is about climate is it's where you live. I think we have our skill in forecasting the mean temperature of the planet, things like that, are going to be pretty good 50 or 100 years from now, if we know what the greenhouse gas is going to be like. Unfortunately, forecasting what's going to happen in particular places is much more complicated. And we have run our climate models. I was at a talk just recently where somebody from the National Center for Atmospheric Research ran a whole bunch of climate models and looked what was happening at individual locations. And there's a tremendous amount of variability there, which means there's a lot of uncertainty. So, we can do climate change forecasting, but for the globe, well, we can get a pretty good idea, I think, if we know what the greenhouse gases are. But what's going to happen in specific locations is much more difficult. And one thing that a lot of people don't think about, what location of the world will global warming be weakest and slowest?
Equator.
Here. We are in a place, around here is a location. The west coast of the United States is a place where global warming will be slower, weaker than most places. And the reason is the Pacific Ocean. All the general circulation models, all the climate models indicate that the Arctic will warm up more faster than the rest of the planet. That makes sense because the snow and ice will melt away. The continents warm up more than the oceans because, oceans, it's slow to warm up the water, you know that. And it turns out the eastern oceans warm up more slowly than the western oceans. We are downstream of the eastern ocean. Our weather is dominated by the Pacific. And because of that, global warming will be slower here. It'll take more time to happen. And, if you look at the temperatures of the eastern Pacific, it hasn't warmed up any at all in the last 30 years. In fact, it's cooled down slightly. So people who are demanding that they see big changes here in the Northwest, like snowpack disappearing and stuff like that, they're not giving you good information. Here it's going to be slower. And, eventually it will be significant. The younger people in the crowd will see a very different climate here in 2070 or 80 or something like that. But during the next few years, it's going to be pretty hard to see here.
Let's, one quick note, we have cut off, if anybody has a ballot, you're gonna have to save it for next year. So Mark just cut off the ballots. Let's take one from this side.
Okay.
Jim Little from the Oregon Department of Forestry, and very impressed with the modeling that the University of Washington is doing. As you may know, in the summer of 2009, the Oregon Department of Forestry was identified as a heavy user of University of Washington modeling products and was cut off. Our IP address is blocked. We have not used University of Washington modeling information for 2.5 years now, so thus are no longer a heavy user. My question is, what is the threshold for heavy use? And if we promise to stay below that threshold, when can we reinstate it?
Okay. The University of Washington modeling is funded by the Northwest Modeling Consortium. This is a group of state, local, and federal agencies. And they support it. And they have policies. And that is, we put all our modeling online, for free for anybody. People who have grids, who use grids, who want the gridded information, they have to be members of the consortium, they have to pay. But then there are people who get on and hit us really, really hard and degrade the ability of others to look at the products. These people are I don't know what they got, PCs that are just pulling the graphics. Well, the people that hit us really hard and degrade the ability of others to see, those people, the consortium has made a policy of cutting them off until they get down to a more reasonable level. And so I'm happy to talk to you about that later. But you must have had a rogue computer. That's something that was kept on hitting us really hard. You have to hit us very hard before we cut you off. And you should know that we cut other people off too. That does the same thing, including the Canadian Weather Channel.
Let's come back this time.
That was Steve Tuttle.
You talked about some of the errors in models, both from data sources and from parameterization. And I've had this question asked, and I'm not going to answer it myself. Which one contributes bigger to the errors of models, the parameterization or the initialization?
Well, to give you a complicated answer, it really depends on the situation, okay? But once you have enough, at this point, we're really gaining enough resolution for a lot of the features. And so now I think the biggest source of errors are the physical parameterizations, this description of things like clouds and precipitation. We had a field program here in Oregon called Improve, in which we had radars, we had planes. We went out there and measured all the cloud nuclei. We measured the distribution of size of cloud particles, precipitation particles in the Oregon Cascades. And then we compared that against the numerical models. And my friends, it was embarrassing. Although our models are not bad for surface precipitation, what we were predicting in the clouds was just bad news. And we're working on it. But there's a lot of problems with parameterizations. And this is true of forecasting models. This is true of climate models. This is one of the reasons the climate models have issues. That there's a lot of physical parameterizations are problematic still. And that's one thing we have to work on very heavily.
Jim Todd has a question, I believe.
Yeah, Cliff, and on this, all these modeling pretty much focused on the Earth, is there any possibility that this technology will be able to migrate to NASA and what have you to better model climate on Mars and what have you? Would that apply, has that been any direction
Yes, there are people, no, there's actually some substantial groups that are doing exactly that. I mean, there's even a version of the WRF model I use that's Mars WRF. So it turns out we have, in fact, done that. In fact, I've done that. When I was an undergraduate, I worked with Carl Sagan. And I did a I took an atmospheric model, there was only a 2-level model then, and I actually simulated the Martian atmosphere. You know, in fact, I did a paper with Carl Sagan. So I even had to say billions and millions.